Look up at the night sky. What do you see? A bunch of tiny twinkling lights spread across an endless black canvas. For thousands of years, we've looked at this amazing sky, feeling amazed and really curious about where we fit in. We've told stories, drawn maps of star patterns, and made up myths to understand the grand dance of the universe. But underneath what our eyes can see, there's a set of hidden rules, an unseen musical score that controls the movement of every star, every planet, and every galaxy. It's the music of the universe. And its most groundbreaking composer was a humble pattern clerk with an imagination that reached the very edges of reality itself. This journey into the heart of the cosmos doesn't start with a giant telescope, but with a question, a simple yet powerful thought experiment. What if you could ride on a beam of light? What would you see? This was the kind of question that danced in Albert Einstein's mind. He dared to challenge the very basics of how we understand space and time, ideas we once thought were fixed and unchanging. He showed us that the universe is much stranger, more flexible, and more amazing than we ever dared to imagine. It's a place where time can slow down. Imagine you're in a car going 80 kilometers an hour. A friend standing on the sidewalk sees you coming. If you throw a baseball forward at 30 kilometers an hour, your friend will see that ball flying at 110 kilometers an hour. Your speed plus the ball's speed. That makes perfect sense, right? It's simple addition. We add up the speeds. This is intuitive, it's logical, and for most of human history, we thought this applied to everything in the universe. But the universe has one surprising exception: light. Now let's swap the baseball for a beam of light. You're in a spaceship, zooming through the cosmos at 90% the speed of light. You turn on your headlights. Common sense says, add the speeds. But that's not what happens. No matter how fast you're moving, no matter who's watching, that beam of light will always be measured at the exact same speed, about 299,792 kilometers per second, or about 186,282 miles per second. This is the cosmic speed limit, an absolute law of nature. This idea was the cornerstone of Einstein's special relativity in 1905. It was a radical break from centuries of physics. The speed of light is constant for all observers. It doesn't matter if you're moving toward the light source. It doesn't matter if the source is moving toward you. The measurement is always the same. This isn't just a clever theory, it's one of the most tested principles in science. If the speed of light is the universe's one great constant, then time must be its great variable. This is the strange and beautiful result of Einstein's first big idea. He called it time dilation. Simply put, the faster you move through space, the slower you move through time. It sounds like science fiction, but it's a basic part of reality. Imagine two atomic clocks, perfectly in sync. You keep one on Earth, and you send the other on a trip aboard a super-fast rocket. When the rocket comes back and you compare the two clocks, you'll find that the clock that traveled has ticked just a tiny bit slower than the one that stayed home. This isn't a mechanical error or a trick. The astronaut on that rocket wouldn't feel time slowing down. Their heart would beat at its usual pace, their thoughts would flow as normal, and their clock would seem to work perfectly fine. It's only when they meet the stationary observer again that the difference becomes clear. The astronaut would have aged slightly less than the person who stayed on Earth. The effect is tiny at the speeds we're used to, but as you get closer to the speed of light, it becomes dramatic. Time itself becomes stretchy, pulling out for those in motion compared to a still observer. Just like time is flexible, so is space. Special relativity also tells us that when an object moves faster, its length in the direction of motion shrinks from the point of view of a stationary observer. This is called length contraction. Imagine our super-fast spaceship again. As it zips past you, it would appear slightly shorter or flattened in its direction of travel. Of course, to the astronaut inside, everything would seem perfectly normal. The ship's dimensions would remain unchanged from their perspective. This strange squeezing of space is another necessary outcome of keeping the speed of light constant for everyone. Think back to the muons we talked about. From our perspective on Earth, we explained their survival by saying their time slowed down. But what does it look like from the moon's point of view? For the moon, its internal clock ticks normally, and its 2.2 microsecond lifespan still feels just as short to it. So how does it reach the ground? From its high-speed perspective, the distance between the upper atmosphere and the Earth's surface has contracted. The journey is physically shorter for the moon. Time dilation, from our point of view, length contraction, from the moon's point of view. Both explanations are correct. They are two sides of the same relativistic coin, describing the same event from different frames of reference. For over 2 centuries, the world saw gravity through the eyes of Isaac Newton. He imagined it as an invisible, instant force, a mysterious link stretching across the vast emptiness of space, pulling objects toward each other. An apple falls from a tree because Earth pulls it. The moon orbits Earth because Earth pulls it. It was a brilliant and powerful idea that worked almost perfectly. It allowed us to predict the movement of planets and comets with amazing accuracy. But for Einstein, there was a problem. How could this force act instantly over huge distances? This went against his own cosmic speed limit, the speed of light. Einstein offered a completely new and breathtakingly elegant view. Gravity, he proposed, isn't a force at all. It's a result of the bending of spacetime. Imagine spacetime as a flat, stretched rubber sheet. Place a heavy bowling ball in the center. The sheet warps and curves around the ball, making a dip. This curve is what we feel as gravity. Roll a small marble nearby. It won't be pulled by a mysterious force. It will simply follow the curved path created by the ball's presence. The marble moves in the straightest possible line through curved space. Mass and energy tell spacetime how to curve. The curve of spacetime tells matter how to move. Earth doesn't orbit the sun because of an invisible rope. The incredibly massive sun creates a huge dip in the fabric of spacetime. Earth is like that marble, constantly rolling around the edge of this cosmic well. If massive objects bend spacetime, then what happens when those massive objects move? Einstein's theory made another amazing prediction. He guessed that accelerating massive objects should create ripples in the very fabric of spacetime, much like a boat moving through water creates a wake. These ripples, called gravitational waves, would spread outwards at the speed of light, carrying information about cataclysmic cosmic events. For decades, this idea remained elusive. It was thought the waves were so weak, so tiny, that we could never detect them. Imagine a gravitational wave from a distant collision passing through you right now. It would stretch and squeeze everything in its path. The room you're in, the Earth, even your own body. But the effect is infinitesimally small. The distortion would be smaller than the width of an atomic nucleus. Detecting this took an unimaginable feat of engineering. Scientists built the Laser Interferometer Gravitational Wave Observatory, or LIGO. It consists of 2 facilities, thousands of kilometers apart, each with 2 long arms forming an L. Lasers are bounced down these arms, their light combined. Normally, the light waves cancel out perfectly. But if a gravitational wave passes through, general relativity doesn't just describe the gentle curves of spacetime around planets and stars, it also predicts the existence of places where spacetime becomes so warped that nothing, not even light, can escape. These are the objects we call black holes. A black hole is what's left when a very massive star runs out of nuclear fuel and collapses under its own immense gravity. The star's matter is crushed into an infinitely small point called a singularity. Surrounding this singularity is a boundary known as the event horizon. Once you cross the event horizon, the space-time curvature is so extreme that all paths lead inward. There's no escape. For a long time, black holes were just theoretical monsters, mathematical curiosities of Einstein's equations. Finding one was a challenge, because by their very nature, they are invisible. We can't see them directly. So, how do we hunt them? We look for their effects on the space-time around them. We can detect a black hole by observing stars orbiting what appears to be empty space. We can also see matter being pulled into a black hole. As the gas and dust spiral inward, they form a superheated accretion disk that glows brightly in X-rays, a telltale sign of the monster lurking in the dark. One of the deepest predictions about black holes concerns how time behaves near the event horizon. As you get closer to a black hole, the intense gravity causes time to slow down dramatically compared to a distant observer. If you watched a friend fall into a black hole, you'd see their clock tick slower and slower. More than 100 years after he first thought them up, Einstein's theories of relativity are not just old ideas. They are living tools, super important for how we explore and understand the universe. Every time you use GPS, you're relying on fixes made possible by special and general relativity. Without them, the system would fail. These theories are woven into the fabric of our modern tech world, often in ways we don't even notice. From particle smashers that break atoms apart at almost the speed of light to nuclear power that lights up our cities, the equation E equals mc squared is a constant reminder of how useful relativity is. But its impact goes way beyond just technology. General relativity is the bedrock of modern cosmology. It helps us understand the birth, the growth, and the final end of our entire universe. It's the theory that describes the Big Bang, the stretching of space, the making of galaxies, the life and death of stars, and the mysterious nature of black holes. When astronomers look at the sky through powerful telescopes like the James Webb Space Telescope, they are looking back in time. seeing galaxies as they were billions of years ago. The light from these far-off objects has traveled through an expanding universe, its path bent by the gravity of everything it met, a journey perfectly described by Einstein's equations. And yet, the story isn't over. Relativity, for all its power, isn't the final answer. We know it doesn't quite fit with our other big theory of the universe, quantum mechanics, the science of the super tiny.